So Shubman, Diganta said he would join, didn't he? Shubman?
Yes, sir.
He did, no?
Yeah, he joined.
Oh, yeah, okay, good. Yeah, I think we'll wait till 5. You can get started at 5:05, exactly.
All right. So should I start?
Yes, please. Yeah, I'll start recording.
Yeah.
Yeah, you have to share your screen.
Yeah. Can you see my screen?
Yes. I hope everybody else can too.
All right. So then I'll begin.
Yes, please.
Is it full screen?
Yes, it is.
All right. Okay. So the name of this paper is Formal Verification of Piecewise Linear Feedforward Neural Networks, and this paper was published in 2017. So it's not state of the art right now. It's like some time back this was published. And this paper tackles the issue of formal verification of neural networks where the nodes are piecewise linear activation functions. Uh, Specifically, this paper looks at linear activation functions, which are ReLU and Maxpot. Okay. And this paper is also called the Planet paper, which is like the tool that they use to ultimately solve. So, like, that's popularly known as this paper is popularly known as the Planet paper. So anyway, the main overview is that the idea is to tightly integrate a SAT solver with a LP solver to address these piecewise linear nodes. And we do this in the following way. So we do a linear over approximation of the overall neural network behavior, which is similar to something we have already seen in class, where we do sort of like a triangle approximation. And then we do irreducible infeasible subset analysis based on elastic filtering. And I will explain all these topics, all these points in much detail later, just to give you a heads up of what's to come.
Yeah.
And
You said that you something that we've already seen.
yeah,
Can you name? You meant the crown. I mean, correct? The alpha beta crown, the linear over approximation, the triangular linear over approximation.
right. That, and also in
Diganta,
like deep poly,
deep poly. Okay. Yeah.
right? Like the sort of triangle approximation, like the linear over approximations for those non-linear nodes.
Mm.
Right. So yeah. So this paper basically does these adds these four novel features, which is like the linear approximation of the overall neural network behavior, irreducible infeasible subset analysis based on elastic filtering, and inferring possible safe node phase choices from feasibility checking of partial node phase behaviors, and performing unit propagation like reasoning on the node phases. Right. And so all of this will have dedicated sections for describing what they actually are. And yeah, so that's to come. So just to give you an overview, right? So formally, a neural network is a network which would have a set of nodes, edges, weights, biases, and types. And types is basically means if it's an input node, linear node, ReLU node, or a Maxwell. And the overall neural network can be thought of as a function which takes an input from Rn and outputs to Rm. And if it's an input node, the value that we have given is the value of that particular node. And for linear nodes, what we mean is that the value of that node is the weighted sum of its incoming nodes and bias term. And for all nodes which are of ReLU type, we take a max of this above term with 0. And for Maxpool nodes, we just take the max of all its incoming edges. I mean, the max of all its incoming neighbors. So this is basically the output function. If x1 to xn is the input, this is the output. And AV is the approximate value of the node, which we will assign. This is the assigned value of the node that we are going to calculate. And phases, like ReLU nodes are said to be in less than equals to 0 phase if its assigned value is 0.
I didn't quite understand what you mean by the assigned value.
Right. So assigned value is so the value that we would like infer from our calculations, basically.
So it's the whatever over approximation, not the actual value.
Right. So this is so this is a approximate value of the
Okay.
Yeah, this is the result of our calculations. All right. So for ReLU node, if the weighted sum of its incoming nodes plus bias terms is less than equals to 0, then we say it's in the less than equals to 0 phase. Otherwise, it's in the greater than equals to 0. And similarly, for a Maxpool node, we say it's in this edge phase if that is the edge which correspond to the highest incoming neighbor. So basically introducing, I'm telling you what phases mean, because phases will have, we're basically trying to figure out what are the phase fixtures in the neural network in slides to come. So this is what we are actually trying to verify, that given a feed-forward neural network G that implements a function from R to N to R to M and a set of linear constraints over the real-valued variables x1, xn, which are the input variables, and y1 to ym, which are the output variables. The neural network verification problem is to find a node value assignment function A, the one that we were talking about, for V that satisfies tau. Tau is a set of Boolean combination of LRA constraints. So our job is to find a satisfying assignment A for the set of variables V, which fulfills tau over the input and output nodes of G, for which we have f of x1 xn equals to ym y1 yr. This is basically that this neural networks behaves the way that we should and has a satisfying assignment. And ought to conclude that no such value assignment function exists. So tau contains a Boolean combination of LRA constraints. LRA basically means linear inequalities, and which we would get by basically doing those over approximations. Also, it would have SAT over approximations. So there exists two parts in this picture. One is a SAT solver, which would give me an over approximation of the strictly purely Boolean constraints, and the LP solver, which is an over approximation of the LRA constraints, the inequalities. So to give a pictorial overview. So we have this set of phi. Phi is the purely Boolean set of constraints, which is being solved by the SAT solver. And it's the LRA constraints, which we are generating by doing the over approximation, will be fed to the LP solver, which will get an LP instance, try to find a solution to that LP instance, and return the result back to SAT, to the SAT solver. And if it's going to check if it's SAT or if it's not SAT. It's basically is the like big picture understanding of what is happening under the hood. So now what we're doing is we're doing an over approximation, right? So it's fairly easy to see that soundness is satisfied by the verifier, right? But for completeness, we need to refine our over approximation. So that is done by a modified branch and bound method. So information from the SAT solver is used to create tighter over approximations of the LRA constraints. And the LP solver in turn returns a tighter solution, which are fed to the SAT solver to create a tighter Boolean approximation. And but the question remains is like, how do we over approximate and how does the information transfer take place actually? So any question up till this point?
Now, one question I had was maybe you can, go back to that slide where you define what your assigned value is.
Mm-hmm. This one?
Yeah. So I wanted to stare at that a little bit. AB. So what is the significance of these? I mean, these are the only two kinds of activation functions that.
Right. Only ReLU and max.
I see. I see. Okay. So the problem is how do you? Yeah. So you have to over approximate, and these. So the over approximation function is divided into these phases. Yeah.
Right.
And you have to assign some value for each of those phases or something constraint for each of those phases that defines the over approximation such that your property is still preserved.
Correct. Yeah. Right.
Okay, but you have not said what is the form of the shape of the over approximation is.
Yeah, that is true. That is coming in the future slide.
Okay, later on. Okay.
Yeah. So this is basically the strategy that this Boolean SAT solver gets this set of purely Boolean clauses phi, and it's trying to solve them and trying to find basically at the end of the day a partial node fixture for which it's sending it's calling a SAT solver, and SAT solver is returning some results, and it's checking that if the LRA constraints are also satisfied. If all of them are satisfied, we return SAT, otherwise unsat. Right. And so the question is, how do we over approximate and how does this information transfer actually take place? So this is the shape of this over approximation. So for the ReLU nodes, you can see.
What do you mean by the transfer of information? Transfer of information from what to what?
Right. By that I mean this Boolean SAT solver is going to transfer some it has found that a partial node fixture is satisfying some Boolean constraints phi. So it will transfer that set of node fixtures to the LP solver. And the LP solver is going to infer additional stuff from that partial node fixture and send that additional knowledge that it has found out back to the SAT solver. The SAT solver will then use it to find a bigger partial node fixture, and this process will keep on happening until we find a complete assignment or not a complete assignment. And how exactly is this, what exactly is the Boolean solver finding? What exactly is it sending to the LP instance, and what is the LP instance giving back is again deferred to a future slide.
Okay.
All right. So yeah. So this is how we are basically over approximating. So we are over approximating on the basis of this diagram basically for ReLU nodes, which is that let D be the final value of the node. If L and U are known to be its lower and upper bound, then we know that the value we allow D to have a value in this area. And we see this is an over approximation because this shaded area is always greater than this the values that it can actually take. Right. So this is formally given by these three inequalities. And for the max pool nodes, we approximate with the following constraint. So we say that D is greater than or equals to Ci, and we say that C1 plus Ck is greater than or equals to D plus sum over I2 I equals to 1 to K Li minus max of Li. So this can also be shown to be, hold this. Okay, we can also see that we can convince ourselves that this is true, and this is also true that this is a sound over approximation, and we add this. Basically, we like this is the over approximation that we are doing, and with this over approximation, we add these linear constraints. Sorry, we add these linear constraints as our linear over approximation for these nonlinear behaviors that the max pool node and the ReLU node was providing to us. And by doing so, we have some LRA constraints and we have a LP instance. So after the linear program that approximates the behavior of the overall network has been built, we can use it to make future approximations even tighter. How do we do that? We do that by solving for every node the resulting linear program, which are basically these instances, like these constraints, with the objective function being 1 times V and minus 1 times V for each node V. And what we're trying to do is we're trying to minimize this and we're trying to maximize this. So basically, we're trying to find a tight lower and upper bound. So this is new lower and upper bound for each node, which can be used to obtain a tighter linear program. So whenever new upper and lower bounds have been obtained, they can be used to build a tighter linear network approximation, which in turn allows us to obtain new tighter upper and lower bounds. And the whole process can be repeated several times until the lower and upper bounds cannot be tightened any further. And this process does converge. We do get upper and lower bounds, which we cannot improve upon. However, the authors use a heuristic to break heuristic breakpoint to stop this process. All right. And yeah, so these were the LRA over approximations that we talked about. So what about the Boolean over approximations? So these are the Boolean clauses that we are also going to add. So we basically, what is this saying is that this phi is my is the variable which is going to store all my Boolean over approximation, all my Boolean clauses. So it's saying that all nodes which are of max pool type should have at least, it should be like its phase should be assigned to one of the valid phases. And it should also not be the case that it's assigned more than one phase. Similarly, for ReLU nodes, it should be assigned either less than equals to 0 phase or to a greater than equals to 0 phase, but it should not be assigned both less than equals to 0 and greater than equals to 0 phase. So with that, we go basically, this is what we are doing. So this is the previous picture, but with a little bit of more detail added to it, which is that we have a Boolean phi, which is this over approximation that we talked about in this slide. And then we are feeding that, and then we are trying to feed into the LP solver a partial node fixture, and we are trying to find out if that partial node fixture, is it possible to be solved? Is this partial node fixture possible? Does the LRA constraints allow us to keep this partial node fixture, or maybe improve upon it? Okay, if it's this is the branch and modified branch and bound step. So we are trying to see if this branch of the computation, if tree is like, working, if it's like, is it feasible? If it's feasible, then we keep it and add it back to our set of learned clauses, or else we discard it. And how do we do so? So those will be explained in some slides, which is to come in series right now. So this is a classical SAT solve. Okay, and we are basically trying to see, we're going to see how exactly is the LP solver tightly integrated with this SAT solver. And basically this picture is going to get more and more complicated, because we're going to tightly integrate the LP solver, use LP solvers, what the LP solver has inferred to send it back to this SAT solver, and what the SAT solver has figured out to give it back to the LP solver. Right. So this is a classical SAT solver. I'm just going through it once. So given a set of Boolean constraints, which is phi, and p, which is a partial node fixture, which is right now empty, and this variable extra, which we will ignore for now, which will come in handy later, which does unit propagation, conflict check, analyzing conflict, backtracking, and if it's there is no conflict clause, then it guesses p through some heuristics, and then it does extends p and does this whole step of unit propagation, conflict check, analyzing conflict. And if it's actually facing a conflict, then it modifies p, backtracks, and so on, like a classical unit classical SAT solver does. And if we see that no such p exists which satisfies phi, then we say it's unsat. Now, this is the first step of integration. What we do is that we try to check when the conflict clause, when we see that there is a conflict. When we say there is no conflict, we try to see that means that the SAT solver is telling us that from our end there is no problem in this partial node fixture p. See if this SAT solver can find any problem with the partial node fixture p. So then the LP solver can find a problem with the partial node fixture p. So the LP solver takes this p, which the SAT solver has given to him, and tries to figure out if this is indeed feasible. So if it's feasible, then it sees if it's a complete assignment. If yes, then it says SAT. Otherwise, it extends P, like with the heuristic that the original SAT solver had. So for example, in this paper, Planet used the SAT solver MiniSat. So this would guess P in this slide. Is basically going to use the same heuristic that MiniSat would use. And that would feed back into this.
Yeah, Shubman. So it's been, for the rest of the people, it's been quite some time since they saw, it's a long time ago they did see the SAT solver structure. So just to remind them, I'll ask a question Okay, that I hope you can answer. The left part, the left-hand side part of this picture, which returns, either unsat or it can return sat, correct? Now
Right.
that part is only taking the Boolean part, right? That's the
Right.
Boolean abstraction part of it. So then, if there is a feasible assignment, then the LP checks that, correct?
Right.
It can be multiple LP checks.
Right.
And so that gives some values, okay? And what is the guess P bubble
Guest
here?
P is basically when the LP solver has been handed over some P from the SAT solver, and it checks whether this P, like this
Yeah,
partial load
presumably
fixture assignment.
the LP solver gives not only checks some feasibility, whether that constraint is feasible, but I'm assuming that it also gives some satisfying instance, or does it give lower and upper bounds? I mean, does it give
No, it actually gives you a satisfying instance of P.
correct?
Like it
Yes.
basically, so given a P, it tries to extend P through
Mm.
himself, like the SAT solver itself extends P, but it can only do so up till some point, and then it gives control back to the the LP solver extends the P up till some point, and then it gives control back to the SAT solver, and then the SAT solver extends P using their own heuristic.
It's the extend P that I didn't understand. What does it mean to extend P?
Right. So, for
Uh,
example, when we did this in class, so for example, a possible heuristic could have been a preference for which all variables, a preference ordering for which all variables we want to be, uh, get sat. So, some sort of heuristic of that sort, where you basically
ah,
like given a
oh, okay. So you guess for a new variable, yeah, because it's no
right, right.
but yeah, you check it's feasible. So there's no complete. It's not, but it's still not fully sat. That's why you do, and then you guess for a new an
Right. So, for
assignment.
example, yeah.
Yeah.
So
Mm.
for some variables we have already assigned true or false, but for
Mm.
some variables it's still not assigned true or false, right? Because
Mm.
it's only a partial load fixture.
Mm.
And
Mm.
so for some other variables we will now assign it to be true, and then check it if this new extended partial assignment is correct or not.
Mm. Mm.
And so what are the guess piece? Nothing. Just we are giving control back to the SAT solver so that they can choose what variable they want to,
Mm.
extend next.
Okay. But this does not refine your over approximation. This is once you decide on an over
Oh no,
approximation.
no. This doesn't do that. That's going to happen inside these bubbles called
Ah,
check LP, learn conflict clause, and another bubble which I'm going to introduce in the next slide.
okay, fine. Now that gave me. This is just the basic interaction between the DPLL part and your
Right.
LP part. Yeah. Okay.
Yeah,
Good.
yeah,
Yeah.
yeah.
I hope the rest of you got it as well. Yeah. Okay.
Sure. So so yeah,
Yeah, I
so
think just make sure that nobody else has any question at this point before moving on to the next slides. I think.
yeah.
Yeah, I think it's yeah, people should ask. Okay, so because this is the basic DPLLT structure that you saw in class in one of my lectures. It's been
Yeah,
quite
yeah.
some time since that time. Okay, but yeah, this is how it works. The DPLL guesses a partial assignment, which is checked to see if that assignment is feasible in the LP. If it is feasible, then you're done. Okay. If
Yeah.
not, then you will have to guess the assignment for more variables, and then keep doing it. Yeah.
Right.
Yeah.
Yeah. So this is basically it. So yeah, so that's what we're doing. And if it's infeasible, we would learn some conflict clause and then add that to phi. Or if it's feasible, we just ask ourselves this question, like the NP asks itself this question, like if it's a complete assignment, if yes, then SAT, if else, we're going to extend it. And now, when it's feasible, we're trying to introduce a new bubble.
Yeah,
Oh,
but the
before
thing
that,
is, go
yeah.
ahead. Go ahead. I'll ask the question later on, because typical LP solvers,
Mhm.
you say that you add a clause. Okay, so this
Mhm.
adding a clause, it's somehow analyzing the infeasibility. The LP is analyzing the infeasibility and then coming up with some constraints. Usually,
Right.
LP solvers don't automatically do that, do they?
Oh,
Okay.
yeah. They don't. And this is where this, like, these,
There is a
the group of authors are gonna use this LP solver to somehow come up with when it faces infeasibility, they're going to add additional clauses to the set phi.
Yeah, and these clauses are some inequality constraints, correct?
Right.
Yeah.
Yeah.
Okay. I mean, their clauses are just conjunction of inequality constraints. I presume it's conjunction, or they are actually clauses. See, because clauses means it can be any Boolean structure. Okay.
Yeah.
So that's what I mean. One question I have back in my mind. So does
now when it's adding back to phi, then it would be basically conjunction of Boolean clauses.
Yeah. So the infeasibility is due to some conjunction, and therefore it adds some negation of that, and that becomes a clause. Yeah. Yeah. Okay.
And this all will be like, so there'll be like a few slides dedicated to what's actually happening inside Learn LP, Check LP. And so you actually realize what are the clauses which are being added.
Yeah. Okay.
Okay. So yeah. So now the question is, how is the clauses added, right, to phi? So it's basically added by using this thing that I introduced earlier and told you not to worry about, but now it's come to the forefront, which is called extra. So extra is this place where we are gonna add these clauses that we learned from the LP solver, and this extra subroutine is going to add stuff to this SAT solver one by one, and it's going to do that unit propagation, conflict check, analyzing conflict, backtracking, until all the clauses from extra has been exhausted. So what we're going to do is basically take this clauses that we learned from the LP and integrate back into phi, and do unit propagation, conflict check, and analyzing conflict on them as well. And we're gonna so this was the invisible, if check LP check is infeasible. So what if it's feasible? So if it's feasible, then we're gonna learn some additional clauses, and then we're gonna check if the partial node phase assignment that we have is learning it satisfies all the clauses in extra as well. If it does, then we check if it's a complete assignment, and again going back to that tree, if it's not a complete assignment, then we extend P. So if it's not satisfying all the clauses in extra, then we go back to the SAT solver and try to give them back what we have learned already, and basically give control back to them to give us back a new P by modifying the P that they have given us. So that's what's happening here.
Yeah. So question is, in the case where it adds, even when it is feasible, it may learn some new facts.
Right.
And then it adds. So all the new facts that are added true conclusions, correct? I mean, they are
Yes,
true.
yes. They are true conclusions.
Whereas the other thing that is being added is you are how to fix the infeasibility. Okay, so that's the difference.
Right.
Yeah.
Yeah. So this is basically the whole flow of the toolkit. And also there's one more additional learning which they are going to squeeze in here, which is before this P is being sent to the LP solver, that is the partial node fixture from the SAT solver is being sent to the LP solver, they're going to learn some implied phase from the structure of the neural network. And they're going to add those true facts again to extra. And yes, that's basically the whole structure. And we're going to come back many times to this picture, so to show where everything fits into this bigger picture.
So they can add some new learned clauses even when there is no conflict. You don't have to wait till you get a conflict.
Right. Some true facts will be apparent just by the structure of the neural network. Right. So so now this is the check LP slide that we are talking about. So this is what's happening under the hood of the check. So given a phase picture for all relevant maximal nodes in a network, checking if there exists a node value assignment function with these phases and such that all the verification constraints psi is fulfilled can be reduced to a linear programming problem. So for all the partial node phase fixtures that we have been given, so if that partial node phase fixture says that a particular node is in less than equal to 0 phase, then basically we just add this constraint, which says that if it's in less than equal to 0 phase, then the value of that particular node will be 0, and the in sum of incoming nodes, weighted sum of incoming nodes plus bias is less than equal to 0. And also for all the greater than equals to 0 phase selected from the red node, we say that the weighted sum of those incoming nodes plus bias has to be greater than equals to 0. And for all nodes which are of the max pool type, we just say that the value at the particular node is equals to the value of the v dash, where the phase is v dash comma v. Right. So this was the check LP instance that we were talking about. So now we have this set of linear LRA constraints, and now we are gonna run an LP solver with these additional clauses that we added for each variable in our partial assignment P, and see what we get. So now if we see that the resulting linear program is infeasible, then we can discard all the extensions to the partial evaluation from consideration in the search process. And this is done by adding a conflict clause that rules out the Boolean encoding of this partial node phase selection. All right. But the thing is that we can potentially learn a shorter conflict clause. So we do that by this process called elastic filtering. So what is that? So that is basically, we are gonna weaken our set of linear inequality. So for example, if we have this linear inequality, which says that the weighted sum of the incoming nodes plus bias terms is equal to 0, we're going to add a slack term for each such inequality. We're going to add a slack term for SV for that particular variable. And this is weakening this linear inequality. And so if we do this for all the linear inequalities, then for some value of SVs, this resulting set of linear inequalities will become feasible. Right. So then what we are doing is we are trying to minimize a weighted sum of those SVs, the slack values. So we are running the LP solver again with the objective function being the task of minimizing a weighted sum of the slack variables. Okay. And after we run this new LP solver, we are going to see get a ranking of the nodes by how much they contributed to the conflict. That is, we're gonna order the slack variables according to the value that the solver returned for them. And some value slack variable will have a 0 value, signifying that that linear constraint did not need to be weakened. So they did not add anything to the conflict. Whereas some linear inequality had to be weakened a lot. So they would have a high slack value. So what we do is that we take the slack variable with the highest value and then set it to 0. And then what we are doing, we are making the corresponding constraint strict. And we're going to keep repeating this until we get, again, an infeasible LP instance. So by doing so, notice what we're doing is that we are trying to enforce a smaller set of linear inequalities, which enforcing which we are getting an infeasible set. So we are basically getting a smaller subset of the linear inequalities, which originally give us a infeasible set. And we would want this because then we can block off that branch of the SAT solver check, and the smaller clause we get, the better. Right. So this is the learn LP conflict part in the big picture.
Yeah, I think it's a good time to pause for questions if there are any.
Sure.
Yeah, some examples would have helped. Okay, is what I feel. So it's a little bit. I mean, even what I did not completely get it is how the slack variables will reduce the conflicts.
So the idea behind here is that the slack variables are basically the slack variables. The value of the slack variables is basically how much you need to reduce this left-hand side such that this linear inequality would hold.
Correct. Yeah. So
right. So if my slack,
yes,
and then what I'm doing is that I have assigned some slack values for each such linear inequalities. I have given a slack value and not given it a value of the slack variables yet. But I'm then running this LP solver with this new set of linear inequalities with the slack variables, with the objective function being what is the minimum weighted sum of the slack variables. So that is what is the least amount of weakening that I can do to make those set of linear inequalities feasible.
Yeah, now I think I understood. I mean, maybe the rest of, so which means that this is how you generate those extra things, correct? Yeah.
Right.
Yeah. Yeah, such that this thing happens. What if it is not, I guess,
infeasible?
Yeah, if it is not.
Yeah, so that will be addressed in a later slide, where the case where it's actually feasible. But there also we can show that there some new clauses can be figured out. Yeah.
Yeah. I hope others got it. So this is by adding these things and then you optimize this one, you're getting some new, ways you could kind of, by relaxing those things, you can actually fix them, correct?
Right.
Yeah.
And then what we are doing basically is that then we have got the minimum weakening that we need to do to make these variables, this set of linear inequalities feasible. Then after that, we get a set of such slack values, right? And then we are making one by one some of these linear inequalities strict again. But how are we doing that? We are checking which slack value, slack variable has the highest value. And then we're making the corresponding linear inequality strict. And then we keep on doing that until we have found an infeasible set again. At which point we have found, okay, I made these linear inequalities strict, which has led me to finding an infeasible set again. Then these set of linear inequalities and the partial node fixture corresponding to these set of linear inequalities are problematic. I mean, make a conflict clause saying that do not this is a infeasible set of partial node fixtures, so that, and send it back to the SAT solver so that they learn this fact from this tree of computation, this branch of computation.
Yeah, in that sense, this work is kind of more comparable to ReLUplex than deep poly, no?
Right, and it's a yeah.
Yeah, that's actually, I mean, an interesting point there. So I feel like it is more comparable to ReLUplex, but ReLUplex is not doing any overt approximation,
That
right?
is right.
Right.
Well,
I mean,
it is
not in the LRA side of things, at least.
Correct. Not in the LRA side of things. Yes.
Yeah.
Yeah. But deep poly, what it does is it just does 1-over approximation,
Yeah.
for each of the nodes, and then checks.
And then if
it works, it works. Otherwise, it does not do.
Right.
Yeah.
Whereas here they're doing some sort of refinement, like DPLLT like kind of refinement algorithm, right? Where they're doing not just are they refining the LRA based on some phase fixtures, they're also saying that, okay, from this LP can we derive some blocking clauses, and these are things that ReLUplex doesn't do.
Chronology, in terms of chronology, do you guys, when did ReLUplex come? This predates ReLUplex. In terms of chronology, ReLUplex, this work, this you said is to 2017. Deep poly was
that's newer.
Huh?
I think deep poly
is 2018, if I remember correctly, right?
Oh, it's around the same time. Okay, and how about
I think 1 year later. So
ReLUplex was around the same time, isn't it?
Yeah. ReLUplex was 2000.
Deep poly was 2019.
2019, is it? Okay. And when is ReLUplex? Let's just let's see. Just looking that up.
2017.
ReLUplex was 2017. That
right.
I know. So around the same time.
So these are. It seems like this and ReLUplex is sort of like competing papers at the same time.
Right.
In some sense.
And but the thing is that ReLUplex only talks about ReLU nodes, but this also talks about maximal nodes.
Yeah.
Yeah, the kind of refinement here is LP base is much more powerful, it seems like, than ReLUplex. I mean, first of all, ReLUplex only works for ReLU, and it just fixes it. It just So it is not. This is based on LP constraints, the way that it is doing it. Yeah. Okay. So I hope, I don't know if you later on, I mean, I'll wait till then. I mean, what kind of experiment results they actually do?
Yeah.
And
so you have some slides.
Pretty
right?
interesting slides reporting the experiment. Yeah.
Yeah. Any other questions from people? I mean, I know that this. Okay, please go ahead.
Yeah. So this is when it's infeasible. So now, coming back to the picture, this is when it's infeasible. Then we're adding this new learned conflict clauses to extra, and now we're going to look at what's happening when the resulting LP instance is feasible. So if the partial node fixture is feasible, then we define an optimization problem that allows us to infer additional infeasible and feasible partial node fixtures when checking some other partial node fixtures for feasibility. So we're going to use this objective function, which is given a partial node fixture of V dash, which is a subset of V, we're going to maximize this objective function, which is basically like so if the type of the node is a ReLU, then we are trying to like decrease the value of that variable, and also same for if the value is max. So remember, we always did over approximations, right? So this is where we are trying to like tighten our over approximation. So that's why it's trying to reduce the values of the ReLU nodes and the max pool nodes. So this choice asks the linear programmer solver to minimize the error for the ReLU and max pool nodes. So now if we get any tight node from this like this LP solver, and by tight I mean that the error is actually 0 from the actual value of the node, then we can include them in a partial node phase assignment as well. And we basically learned some new partial node fixture. And also we can, this, and also they can learn another additional clause, which is for all those ReLU nodes which are not tight, we would have that their assigned value is greater than equals to greater than 0, right? And yeah, this is basically reminding you that this was always an over approximation, right? So in those cases where the assigned value is greater than 0, then we know by choice of the optimization function and the fact that we performed the analysis in a linear approximation of the network behavior, that some node in the vertex set needs to be in the greater than equals to 0 phase under the partial valuation P. So this is basically, one can actually check this out, and this actually holds true. That this needs to be the case, that if we have a node which is not tight, that is after running the LP solver, we have seen that the assigned value is greater than 0, then that means some node in my vertex set under the partial valuation P must have been in the greater than equals to 0. And so they add this clause as well to the to 5. Yeah, you were saying something?
No. Sorry, that was distraction. No, go ahead.
Oh, sorry. Yeah. So they add this node as well to extra, and yeah. So that's the additional bit of clause that they squeeze in by this process. So yeah. So this is this learn additional clause, and then yeah. So then we go back to checking if P satisfies all clauses in extra complete assignment. So now the only bubble which is left to be talked about is this learn implied phase from structure and add to extra. So what does this really mean? So right. So yeah. So this is basically, consider this example where this node is this is a ReLU node. This is a ReLU node R1 and R2, and M is a max pool node, and the value of R1 is between 0.0 and 1.5, and the value of R2 is between 0.1 and 2.0. This we know somehow by our analysis that we have done already. When this is being sent here, we know already the lower bounds and the upper bounds, and this lower and upper bound for R1 and R2 comes out to be 0.0 and 1.5, and for R2 is 0.1 to 2.0. So R1 can be in less than equal to 0 phase or greater than equal to 0 phase, but we can already see that R2, if we know the lower bound is 0.1 and 2.0, it has to be in the greater than equal to 0 phase. Right, and similarly, so then if at some point the SAT solver decides that the node R1, okay, should be in the less than equal to 0 phase, this fixes the value of R1 to 0, right? Because it's a ReLU node. And since the flow out of R2 has a lower bound of greater than 0, So this is a question like, what should be M's phase?
Mhm.
Like, if anyone wants to answer, that would be great. So R1 is basically in the less than equals to 0 phase.
Mhm.
R2 we know is from 0.1 to 1.5, right? 0.1 to 2.0. So what should be the value of, like, what phase should M be?
Should be greater than 0, no?
No, M is a max pull phase, max pull node. So it should either be in this phase or this phase. Like this edge should be its phase, or that edge should be its phase. So it should be in this phase.
Um,
Did anyone say something?
I said R2 phase. I don't know if that's.
Oh yeah, exactly. It should be in the R2 phase, exactly. So it should, the M's phase should be set to R2M. Yeah, because it's like obviously, because otherwise M's value couldn't have been greater than 0. So similarly, we can assume that the analysis of the initial layer linear approximation of the network's node function, for example, gives at some point during the computation that M needs to be in 0.5 and 0.7, and the phase of R1 is chosen to be less than equal to 0. Then this would imply that the phase of R2 must be greater than equal to 0, because otherwise then M would be not greater than 0.
Mhm.
Right. So this is what I meant by when I said ki these are the things, some additional clauses which one can learn by the structure of the neural network.
Mm.
Right. So they are adding these things as well in their learned clauses. So yeah, so that's how this whole picture is panning out. Right.
The only tightening, refinement like thing happens in this feasible part.
Right. Learned additional clause. So that's actually yeah, there. Because if it's infeasible, then you don't need to tighten it.
Mm.
Right. Because like the over approximate thing, if the over approximated linear constraints itself is infeasible, then you don't need to tighten it.
Mm.
But if the over approximated LRA constraints are feasible, then you need to tighten it and see if we can get some more feasibility or infeasibility results.
Yeah. So in this the edge where you actually add some new information about what phases are, need to be negative or positive,
Right.
because of some other constraints that you know. How will that help? That can help in reducing the complexity of future checking of conflicts, etc. I mean, I guess it may prevent new conflicts from coming.
Right. It basically means that the SAT solver does not go into does not need to check whether the node that we just implied should be in this phase.
Yeah.
It does not go into the trouble of figuring out that whether that should be in that phase or some other phase.
Yeah, most likely there will not be any feasible solutions in that part anyway.
Right, and the paper also say that this checking, which is this structural detection of implied nodes, this they can do in like linear time.
I see.
Yeah, because it doesn't involve an LP call.
Yeah.
Okay, got it. Yeah. I think you can go till 6:15, huh? 6:20.
Oh, right. Yeah, I'm just left with the experiments.
No, you go. You take your time because we've been giving. You started 5 minutes late only because earlier you used to. Yeah. So I've been giving 1 hour 15 minutes to people. Yeah, I mean for most
Right.
yes.
So yeah, so after this, so this is basically we are done with what the toolkit is. So now we go to experiments. Right. So they implemented this approach in C++, and the toolkit it's called Planet, and it used the SAT solver called MiniSat and the LP solver called GLPK. And they test the tool on the problem of predicting. So they take two problems, basically, like two class of problems, and try to see how this fares in those problems. So basically, they took the problem of predicting collisions between two vehicles that follow curved paths at different speeds and recognizing digits in the Amnes data set. And an interesting point would be, also the neural networks they used are in training are trained using the CAFE framework. The benchmark that they use is
for people
for
that
this.
Don't know. I mean, maybe MiniSat up to for a long time. I don't know if it maybe even it is comparable to Z3. Okay, it was a competitor to Z3. Z3 now I think outperforms MiniSat or something. I don't know. Certainly, it is not just a SAT solver, but actually it's an SMT solver that has LP and everything in it. Correct? Yeah. Yeah.
Right.
Yeah. This is much like Z3.
Yeah, although here I think they just use the SAT part of it, right?
SAT part
Yeah,
is
yeah,
it?
yeah.
So it's only the SAT part that they use with RePail saying they use their own LP. Because they have to
Yeah,
get it
yeah.
out of the LP. But that is their own LP.
Right. And
They
I think
use GLPK. Yeah.
Yeah.
Oh, the linear programming kit. Okay, sorry, I missed that. Yeah, okay.
Yeah, and I mean I don't know if this is not discussed per se, but I think the comment from the Reluplex paper where they are doing this linear programming using floating points might also be relevant here, because any SMT solver's LP solver would probably use actual real values, whereas GLPK and all of these guys will use floating point values. And these people would want to probably use floating point for performance sake, which is what Reluplex does as well.
Yeah, it's possible. MiniSat probably doesn't use that. That's why they want.
Although they don't say this in the paper. I mean, it's just my speculation. Sorry, go ahead.
Yeah. So the benchmark that they use is their own benchmark that they devised, and it's not ACAS XU, which is the standard benchmark people use for collision problems. So what is their benchmark? So they want to find out the safety margin around instances. Okay, so what are the instances? Like the problem instance in a car like this collision problem is that you have two initial positions of, say, two vehicles, their initial velocities, and their rotation speed. And you're supposed to predict whether they will collide. So they want to find out the highest value of epsilon, such that for every instance that is classified as colliding or not colliding, if the parameters, namely initial velocity, initial position, and the rotation speed, are changed, epsilon are still classified the same. Right. So they defined a neural network architecture that consists of 40 linear nodes in the first layer, followed by a layer of Maxpool nodes, each having 4 input edges, followed by a layer of 19 ReLU nodes and 2 ReLU nodes for the output layer. This again is this architecture they borrowed from the CAFE framework. And they obtained 500 such neural network problem instances from the safety margin exploration process, the safety margin being the value of epsilon. So they compete Planet against EIC's.
How big are each of them?
How big are?
So how? 40.
Oh yeah. I think these are like so they
much smaller than ACAS, no?
Yeah.
Much smaller.
So they basically run this on each problem instance. They run this on 3,000 different collisions. Yeah, and which they simulated.
Yeah, sorry.
And which they simulated themselves and figured out beforehand and classified them as colliding or not colliding. You were saying something?
No, that's all. No, I just wanted to compare the size. Of course, the size-wise it is smaller, but of course it has max pool nodes. Okay, and in addition to a mixture of max pools and ReLU nodes, which makes the problem a bit more complicated. No, yeah.
Yeah, I think one more thing that could be said about the size is they also have a larger number of benchmarks. So although they're using smaller networks, they have 3,000 for each kind of network. So ultimately, the total number of benchmarks turns out to be largest. I don't know if that is, yeah, if that is any help to interpreting the experiments, but that is there.
How frequently max pool is used in practice?
So, I mean, in CNNs, they're used very widely.
I see.
Yeah, very, very widely. Almost all CNNs, as far as I'm aware, they have some sort of a max pool somewhere.
Yeah. So
does deep poly work with max pool?
I think deep poly doesn't, but I think this alpha beta crown does definitely works with it. So Crown specifically does work with it. Crown had this thing where they were going to allow any kind of arbitrary activation functions. So yeah, it might take more refinement for those things, but I think they definitely work with max pool.
Okay. Yeah, please proceed.
Okay. So yeah, so they compare Planet against EIC's 2.5.2, which is an SMT solver, and they compare themselves with Gurobi as well, which is an MILP encoding. But also they compare themselves with vanilla EICs and also SMT encoding plus the linear over approximation that these guys talked about, using those triangulations and so forth. And similarly for Gurobi, they compare it against the vanilla Gurobi and also with linear over approximation. So this is the result that they get. So this one at the bottom right is just vanilla Gurobi. This is vanilla EICs. This is EICs with linear approximation, the green one. This is Planet, gray one, and Gurobi with linear over approximation is the blue one. So there are a few things to note here. Firstly, is that without linear approximation, whatever these EICs and Gurobi perform, Planet performs way better than them. But with linear approximation, both Gurobi and EICs perform significantly better than their vanilla versions. Planet does outperform EICs with linear over approximation, but Gurobi with just linear over approximation does perform better than Planet. And they admit that, and they say that this is happening because basically they say that Gurobi is a enterprise software with under the hood heuristics, which might be the reason why they're performing better than Planet. The Planet basically uses an open source GLPK solver. So one might assume that if Planet used Gurobi as their SAT solver, they would have performed better than just Gurobi with linear over approximation. And also another point about the linear over approximation is that this linear approximation, as I said, itself, when added to the vanilla encodings, give them way better performance in terms of time taken. So this is a point of difference from Marabou, which is that the Marabou also does a similar sort of integration with a SAT solver and a LP solver. But it's interesting that just adding the linear approximation itself gives them such performance gains. And maybe this acts as an influence for the triangulation approaches in alpha beta crown as well. Yeah, so that's a interesting food for thought. And yeah, with that, this collision set is done, then we're left with the MNIST data set. So in the MNIST data set, what they have is a one input layer with 28 cross 28 nodes, one convolutional neural network with 3 cross 13 cross 13 nodes, where each node has 16 incoming edges, one pooling layer with 3 cross 4 cross 4 nodes, where each node has 16 incoming edges, one ReLU layer with 8 nodes, and one ReLU output layer with 10 nodes. And again, this architecture they borrowed from the Caffe framework. And first, they want to see whether there is an image that is strongly classified as 2. More formally, what that means is that they wanted to obtain an input image for which the network outputs a vector y0 to yn, for which y2 is greater than or equals to yi for all I. And this delta is a large enough delta. That is, the probability that that image is y2 is way more than the probability that it's any other digit. So they want to see if such images exist for various values of delta. So this is the two that they took, and they wanted to see if there exists an image which is still classified as 2, but with delta equals to 20 and delta equals to 30. So they found for values of delta equals to 20 and delta equals to 30, such images can be found by Planet in 4 minutes 25 seconds and 32 minutes for 35 seconds respectively. For delta equals to 50, no such image can be found. But for delta equals to 35, Planet times out after 4 hours, while Gurobi with added linear approximation constraints could not find a solution in this time frame either. And so these times that they get for delta equals to 20 and 30, they also mentioned in the paper that these are better than, Guessis and Gurobi. And the final thing that they do is they are interested in finding how much noise can be added to the image before they're not correctly characterized anymore. So they start with the digit, which has been correctly characterized by the learner network as a digit 3. And this is that digit 3. But they ask how much, whether there is another image that is categorized as a 4, but for which each pixel has values that are within an absolute range of plus minus 8% of the color intensity of the original image's pixels, where we keep the pixels the same that are at most 3 pixels away from the boundaries. To determine that this is not the case, Planet requires 1 minute 46.8 seconds. But for a range of plus minus 12%, Planet times out after 4 hours. Yeah. And again, this value, they say, is better than what Gurobi and Guessis propose. So this is basically the experiments. So yeah, so that's basically it. If you have any questions or comments,
it's a little bit late, but I'll still allow for a few questions if people want to have a go at it.
Questions or comments?
Shouldn't they be comparing it with, I have a question if nobody else does. How would Alpha Beta Crown, do these kinds of things?
Yeah, I think, I think given the current sort of margin that Alpha Beta Crown has over everything else, I think Alpha Beta Crown would probably be.
Hello?
Yeah, I guess Diganta dropped off.
Yeah, my network just dropped for a second. Yeah. No, so I am saying that of course they don't have some experiments, so we can only speculate. But I think Alpha Beta Crown would probably perform much better because although they don't do any sort of clause learning and they don't have an integrated SAT solver which can potentially use some smart heuristics to choose the branches, their branching heuristic is much more simple. But nonetheless, when they're calculating the bounds, see here eventually for each sort of partial assignment coming from this SAT solver, we have to do an LP call. Whereas in alpha beta ground, they don't do an LP call. They don't need to do an LP call, right? So they can just do some sort of much faster gradient descent based analysis, and from that they'll be able to understand whether it's feasible or infeasible. So in that, I think that is basically what really makes them potentially much faster than this.
Yeah,
But
but
it
I
is an
wonder-
interest. Yeah.
Yeah. Yes, go ahead, finish.
No, I was just saying it would be interesting to see what happens if one would take something like alpha beta ground and replace the LP solver here with the the bounding engine of alpha beta ground. Would we get something that is faster than the current alpha beta ground, simply because of all of these learned clauses and more efficient branching coming from the SAT solver?
No, but I wonder here, this is more effective if you want to prove more expressive properties that have more Boolean structures and so on.
Oh yeah, that could be the case. That could be the case.
Whereas, in the experiments, they've only done it for simple conjunctive greater than or equal to properties. So where you don't need as much of case splitting. Although the case splitting is required for ReLU, it is true that it is required for ReLU, that I understand. But if they're over approximating it, that's another axis of comparison that I wonder if this is more effective for proving properties that have more Boolean structure in it. I don't know.
Yeah, that could potentially be true. Yeah, that is actually, I think, a good point. Potentially, because the SAT solver and its heuristics and all these learned clauses might be helpful if there is a more complicated and richer property, like with more Boolean structure. Yeah.
But whether people really care about such complex properties for DNNs, it is unclear. Okay.
Yeah, that is, yeah. I mean, I don't think people have really figured out, like from the ML community, they also, I don't know if they really understand how to very nicely use these, a tool even like alpha beta ground, which is doing very well in terms of performance, right? But yeah.
Okay, so we ran out of time. Okay, so let's thank Shubman for a good talk and late, and have a nice weekend, and we'll see you Monday.
All right. Thank you.
Thanks, Roman. Great talk.
Thank you.
Bye.